So from the previous video, we sketched the transfer characteristic of the input volt of this network, and that's what we obtained. Now we wanted to bias this clipping circuit, right? So we wanted to place a voltage source over here. So that is the goal of this lecture. So we have a voltage source now in series with the diode, and then we would like to sketch the output voltage and the transfer characteristic. So what we wanted to do is to still make the approximation regarding whether when the diode is on and when the diode will be off. So that is the characteristic of the diode, right? And there's just threshold voltage. That's what we call VD on. Now, so to find the conditions under which the diode will turn on and off, what we're going to do is to assume that the diode is on, right? So when we assume diode is on, so we could assume that the diode is off and do the analysis, or assume that the diode is on and do the analysis. We are going to find the conditions, so it doesn't matter which one you start with. So when we assume that the diode is on, then the input voltage that I call it VI here, right? Excuse me. So we can write a KVL equation and use that to find the condition that relate to VI under which the diode turns on. So we have now let's analyze this network. So we have VI, which is, and then the resistor. So since we assume the diode is on, plus and minus there, and the current to the diode ID we assume to be positive. Excuse me. And we have this bias voltage V. Okay, so we can write the KVL equation. So VI, well, the voltage across the resistor is VR, and this is a VD on. So when I write a KVL equation, I have VI equal to VR now plus the diode voltage plus the bias voltage V. Now the voltage drop across the resistor is RID plus VD on plus VI plus the bias voltage V. So VI, so that's for RID, which is VI minus VD on minus V. So because the diode is on, so diode is assumed to be on, so ID must be positive. That means VI minus VD on minus V must be positive. So in that case, V must be bigger than VD on plus plus the VI must be bigger than VD on plus the bias voltage. Now, so what is the output voltage? The output voltage is taken across, so the output voltage is the voltage across here, so V0. So under this condition, V0 will be equal to VD on plus V, and for that case, VI is bigger than VD on plus V. Excuse me. So that's one condition number one. So for condition number two, we'll have VI, so the diode will be off in this case. So diode is off, and when the diode is off, I mean VI must be less than VD on plus V. So in that case, let me redraw the network. So we have the input voltage VI, okay, which is, and then I have the resistor, and the diode is off. And then I have the bias voltage V, and the output voltage is the voltage across here, V0. Okay, so so what is the output voltage? So the output voltage, so if I write KVL, I will have, so this still be my VR, so VI will be equal to VR plus V0. Excuse me, but the current ID equal to 0, so that means VI will be equal to V0. So under condition number two, when the diode is off, so this is 1, this is 2, so when we put both of this together, what do we have? We have V0 will be equal to VD on plus V, when VI is bigger than the diode voltage plus the bias voltage, and then V0 will be equal to VI when excuse me, VI is less than VD on plus V. So from this point, I think if you're able to watch on the videos up at this point, you notice that once you stick with this process, assume the diode is on or off, write KVL, then you'll be able to correctly solve the network. So I have this kind of sketch the input voltage. So as I'm saying, the input voltage is a sine wave, right? So we have this sine wave over one period. So I'm gonna make videos on when you have square wave functions and when you have triangular wave functions as well. Okay, so here we have, so VD on plus the bias voltage So excuse me. So the voltage when VI is bigger than so when we are in here, right, that's the area where VI is bigger than VD1, then V0 equal to this, then it's equal to VI. Otherwise, when or when the VI is less than VD1 plus the bias voltage. Okay, so the the sine wave is the input voltage, and the red graph is the output voltage. So I'm gonna sketch the transfer characteristic. So the transfer characteristic will look like this. So let me sketch the output voltage as a function of the input voltage. So V0 here, oh no, VI there, the input voltage, and then I'll put the output voltage here. So now let's put VD on plus the threshold voltage. Okay, so VD on plus the threshold voltage there. So VD on plus the threshold voltage. So when the when the input voltage VI is less than VD on plus the threshold voltage, then we have VI. So it's gonna look like this with slope 1. And then it's gonna remain the VD on plus V on for this case. So as you can see, if you look at what we did before, then what we have here is just VD on plus the bias voltage. Okay, so that's the difference. So let's solve the network when the diode is facing up, or when the diode is pointing up. So I'm gonna use the same diode characteristic. Okay, so this is another circuit. So we know that the characteristics of the diode, the IV, so ID here, so VD, the voltage across the diode here. Now the current through the diode there, and we are going to approximate the characteristic of the diode as this. So this will be the VD on. So like we have been saying, we have the diode like that. So the current to the diode and the voltage across the diode. So we can replace it by a constant voltage source, the current ID, and the voltage is VD on. So I am going to assume that the diode is on, and we have our network that looks like this. So we have the resistor, and we have the diode and the threshold voltage V. So this is V. this is VD on, and the current is flowing like that from right to left, and the voltage here is that's what we call V0. So when I write KVL, so what do we have? So the voltage across the resistor, okay, write it like that. So VR got RID. So when I write the KVL, I have VI equal to minus VR minus VD on and plus V. Excuse me. So then we have negative RID minus VD on plus V equal to VI, the input voltage. So RID equal to minus VI minus VD on plus V, and that must be positive because we assume the diode is on. So diode on, meaning the current to the diode is positive. That's our assumption. Excuse me. So that meant VD minus VD on. So in that case, what do we have? We have minus VI must be bigger than minus bigger than VD on minus V. So VI is less than V minus VD on. Excuse me. So under this condition, what do we have? We have V0 will be equal to minus VD on plus V. So for this condition, VI must be less than V minus VD on. Now that's one. Number two, the diode will be off. So when the diode is off, excuse me, when the diode is off, VI must be bigger than V minus VD on, and the output voltage. So what is the output voltage? I'll sketch the network. So we draw the network here. VI have resistor. So the diode is off, and then I have V. So the output voltage V0. So when I write KVL, I'll have VI equal to the drop across the resistor, which is 0, plus V0. So VI equal to V0. So when we put it together, we have V0 equal to VI when VI is bigger than V minus VD on, and then it's minus, so it's V minus VD on when VI is less than V minus VD on. So that's the threshold voltage. So can insert space here. So I can sketch the output voltage. So let's sketch the output voltage. So the input voltage is this. Sound wave doesn't look good, but let's see. So something like struggling with this. Okay, so let's see. This is so VI. Now V minus VD1, that will be so somewhere here. V minus VD1. Okay, so let's assume that V is bigger than VD1. So if V is bigger than VD1, then the difference will be positive. And let's say V minus VD1. So when the input voltage is bigger than V minus VD1, which is here, V minus VD1, then the input, the output voltage equal to VI. So it's going to be this. Then when V is less than VI is less than V minus VD1, then it's going to be constant. So like this. So that would be the output voltage in this case. Okay, so like that. So that's the output voltage V0. So now let's sketch the transfer characteristic. So you can sketch the transfer characteristic. So we have now put the input voltage here, the output voltage there. So let's say V minus VD1. Right, so I'm assuming that V is bigger than VD1. Okay, so to sketch it, right, and V minus VD1. So now when the V is bigger than V minus VD1, when VI is bigger than V minus VD1, which is this, right, on the right, right, then V equal VI. So the we have V0 equal to VI, so which is like mx plus b. The slope is 1, and the y-intercept will be 0, so the slope will be 1, right, slope 1. And then the output when VI is less than VD1, then it will be equal to this. Okay, so the transfer characteristic looks something like this. Well, and then this. It's not drawn correctly so nicely. Right, so that would be the transfer characteristic.